Okay, now in this chapter we're going to learn about and work with complex numbers. Complex numbers are, you take the real numbers and you add one additional number, which in turn actually adds infinitely many more numbers. And I'm going to ask you to just consider the following. We know how to solve equations like, say, x squared minus 1 equals 0, right? We could factor this. It's a difference of squares, and we get x equals 1, x equals negative 1, right? We could find the solutions of that equation. But what if I make a small change to this equation, and I say, oh, it's x squared plus 1 equals 0. Now, this doesn't factor, but you could say, oh, well, we can isolate that square, right? If I subtract 1 from both sides, I get x squared equals negative 1. And this leads us to conclude that, oh, this probably doesn't have any solutions because I can't square a number and get a negative, right? If you square a positive, you get a positive. If you square a negative, you get a negative. And it's true that this equation has no solutions in the real numbers, right? There's no number on the real number line such that when you square it, you'll get negative 1. However, a few hundred years ago, somebody said, well, what if there was such a number? It just is not in the real numbers, right? But what if I have to consider a new kind of number? We call these the complex numbers, and they're also called imaginary numbers. It's kind of a bit of a derogatory term, I think. At the time, people didn't think there was anything, that they were almost just sort of silly to consider because they weren't, part of the real number line that we know and love so much. But somebody said, look, what if this exists? And that mathematician called it I, right? So x equals plus or minus I would be the solution to this. Now, we are working in a technical mathematics book with a lot of engineering applications, and for that reason, instead of calling it I, we call it J. And the reason for that is that in electrical engineering, a variable current, I stands for a current. So we use J, and as you'll see, that'll be true in any, most engineering textbooks, we'll use J as well. So we start with a new definition. All right, we have this new number we're calling J. J is defined to be the square root of negative 1. If I want to refer to the negative J, it's just negative square root of negative 1. And so J is just defined to be the number that when you square it gives you negative 1. It's not a real number. It's not on our real number line. So we're going to begin by simplifying some radicals that involve negatives, and we're just going to express each in terms of J. So the square root of negative 9. When I have, well, I guess I'm gonna sort of do this out the long way and then kind of explain a bit of a shortcut. So this negative 9 is negative 1 times 9, and this is the square root of negative 1 times the square root of 9, and the square root of negative 1, well, that's J, and the square root of 9 is 3. So J3, or usually we'll say 3J. The shortcut of that is that if I have a negative number inside the radical, I just take out the negative as a factor of J, and then rewrite the radical without the negative, and then simplify that. So here in part B, I've got the square root of negative 1/4. So here's the negative. I'm going to pull out that negative as a factor of J times the square root of a quarter, and the square root of a quarter is a half, so we have J times a half, or 1/2 J. And then the square root of negative 5, so I've got a negative in there. I'm going to take out that negative, comes out as a factor of J, and then we just have root 5 left over. Root 5 is not a perfect square, so I'm just going to leave that. Now here I write the J in front of this radical because I think it makes it a little bit more clear. There's no confusion. It doesn't look like, there's no possibility that somebody will think that the J belongs under the radical, which can sometimes happen if we write the J on the other side. Now we have to be careful with our rules of working with radicals here. We know that we've been able to combine radicals under multiplication, and that's how we did a lot of multiplying in the last section. Now we're still allowed to do that, but we cannot combine radicals under multiplication if both the numbers are negative, okay, because that can give you incorrect results. So if we're dealing with negatives inside the radical, the first thing we want to do is just pull out that factor of j. So just apply this property when you're dealing with radicals that involve negatives, and then once you have positives inside the radicals, all of your properties apply as usual, even the multiplication property. So let's begin. We've got here the square root of -4 all squared. So I'm going to do this out the long way, but you could probably have a gut instinct about what this should be, right? We're taking the square root of -4 and we're squaring it, so we should get -4. Let's work this out. So I've got the square root of -4 times the square root of -4. Both of these radicals, I can pull out a factor of j. So j times root 4 times j times root 4. And each of these, let's see, I've got root 4 times root 4, which is 4j squared. And we know that j squared is equal to -1. So we get -4. So, the square root of -4 squared is still -4. Let's try another one. The square root of -3 times the square root of -12. So I'm going to begin by applying that property that says if I have the square root of a negative, I'm going to just pull out that, pull out the factor of j. So I've got j root 3 times j root 12. Now I can combine this product, right? Root 3 times root 12 is root 36. And then I have j times j. So j squared times root 36. The square root of 36 is 6. And j squared is -1. So we get -6. Now let's work on this next one. Look how similar this is to part B. There's a little bit of a difference though. I've got a product just written under a single radical. So order of operations tells me I got to do the multiplication that's in that radical first. So -3 times -12, well, that is the square root of 36, which is 6, a positive 6. So we should just note that these are not equal. And this is what that warning at the top of the page is all about. The square root of -3 times the square root of -12, we can't combine that under a single radical. This is not the same as the square root of -3 times -12. So that property about combining radicals under multiplication doesn't hold if they're both negative. Alright, next we have the negative square root of -75. So, okay, I've got a negative inside this radical. I'm going to pull that out as a factor of j. So -j times the square root of 75. Now 75 is 3 times 5, 25, which is 5 times 5. So it's a square root. I've got a pair of 5s in there. So I could take out a factor of 5. So I get a -5j square root of 3, and I'm actually just going to leave it written like that. Okay. Now let's consider the powers of j. So j to the first is j. J squared, we know by definition, is -1. Now let's keep going. What is j cubed? Well, let's use our properties of exponents. J cubed is j squared times j. We know that j squared is -1. So times j gives us -j. J to the fourth is j squared times j squared, which is -1 times -1, which is +1. So j to the fourth is equal to +1. J to the fourth is real. J to the fifth is j to the 4th times j to the 1st. Now j to the 4th is 1, so this just gives us j. And j to the 6th is j to the 4th times j squared. J to the 4th is 1, j squared is negative 1, so we just get negative 1. And in fact, you see this cycle repeat. So we have these 4 distinct powers of j, negative 1, negative j, 1, and then it begins again, right? So there are only 4 distinct powers of j. I can find higher powers, but they'll all be one of those 4. That pattern continues. So j to the 5th was j to the 6th is negative 1. The pattern continues. So j to the 7th, well, that'll be negative j. J to the 8th is 1. J to the 9th is j again, right? So just this pattern, j negative 1, negative j 1, just continues forever. And we can use this, and we can use the fact that j to the 4th is equal to 1 to help us find really high powers of j. So we're going to start with a small one, j to the 10th. So the first thing I'm going to do is write 10 in a helpful way, what I think will be a helpful way. And I'm going to just think of it as some multiple of 4 and then what's left over. So the highest multiple of 4 less than 10 is 8, and that's 4 times 2. And then there's 2 left over, right? So 4 times 2 plus 2 is equal to 10. I'm going to use our rules of exponents. So for starters, if I'm adding in the exponent, that corresponds to multiplying. So I've got j to the 4th times 2 times j squared. Second, when I'm multiplying in the exponent, that corresponds to raising an exponential expression to a power. So this is j to the 4th squared times j squared. Now the reason this is helpful is because I know that j to the 4th is 1. So what we have here is 1 squared, which is 1. 1 to any power is 1. So I know this has got to be 1. And then, so j to the 10th is the same as j squared, which is negative 1. Now, you might look at j to the 10th and think, well, I could just have extended this power. We were almost there, right? Like we got up to j to the 9th, so why go through this whole rigmarole? And the reason is because then if I wanted to do something like part B, j to the 531, I sure am not going to keep writing out powers of j and following the pattern until I get to 531. What I want to do is take out multiples of 4. And it was all about take out however many 4s will come out and then see what's left over, right? So however many 4s come out, that's going to end up just being 1. And then this part that's left over in the power, that's what we ended up with, right? That's what j to the 10th was equal to, was j squared. That was the important part that was left behind. So I'm going to see how many times 4 goes into 531, and more importantly, what is the remainder. So I'm going to take 531, I'm going to divide it by 4. Bear with me while I do some long division. 4 goes into 5 once. Do some subtraction, that's 1, bring down the 3. 4 goes into 13, 3 times. 3 times 4 is 12. Subtract, that's 1, bring down the 1. 4 goes into 11 twice. 4 times 2 is 8. Subtract, that gives us 3. Now there's nothing left to bring down. This is our remainder. So the division algorithm kind of ends here. And it's that part that's left over. The fact that 4 goes into 531 132 times is not that important. What's important is that there's a remainder of 3. And so this is equal to j cubed. And j cubed is negative j. To see it worked out kind of the long way here, using all of this, I could say that j to the 531 is equal to j raised to the, let's see, 4 times 132 plus 3, and this is j to the 4th all to the 132 power times j cubed, and j to the 4th is 1. So this is 1 to the 132 power, which is 1, and this just gives us j cubed, which is negative j. Okay, so we've been working with just multiples of j, right, and powers of j, but a complex number has can have a real part and the imaginary part. So it isn't just that j and 2j and negative 5j are complex numbers, but 2 plus j is a complex number, right? Or 7 minus 5j, that's a complex number. It's got a real part, that's a real part, the real part doesn't have the j attached, and then the imaginary part is the coefficient of j. So the imaginary part to that number is negative 5. The imaginary part to this number is positive 1. So when we write a complex number in this way, where we have this real part and the imaginary part, we say that it is in rectangular form. Now, two complex numbers, say a plus bj and x plus yj, are equal if and only if a is equal to x and b is equal to y. So they're equal if their real parts are equal and their imaginary parts are equal. So we can use this fact to solve some equations. The first one is really quite simple. If a plus bj is equal to 3 minus 4j, the only way that happens is if a is equal to 3 and b is equal to negative 4. Next, this one has a little bit more going on with it. So I'm going to first just write both of these, both sides of the equation, both of these complex numbers in rectangular form. So on the left side, the real part is 4 minus x. And then we're subtracting 6j. Now there's no reason why I have to use parentheses around 4 minus x. I'm putting them there because it makes it more clear that that is the real part, that that is like a unit, a part that goes together. On the other side, everything, you know, I've got j plus j times y. So it's all imaginary, and so the real part is 0, and the imaginary part, I'm just going to factor out the j, that'll be 1 plus y. So now, if these are equal, that only happens if 4 minus x is equal to 0, which happens when x is equal to 4, and if negative 6 is equal to 1 plus y. Keep in mind, you know, you got to grab the sign that goes along with it. So negative 6 is equal to 1 plus y. And if we subtract 1 from both sides, we get negative 7 equals y. Now, the conjugate of a complex number, we've seen and heard the word conjugate before when we were working with radicals, and keep in mind that j is a radical, it's a square root of negative 1. The conjugate of a complex number is what we get when we change the sign of the imaginary part. So the complex conjugate of a plus bj is a minus bj. It's always changing the sign of the imaginary part. The conjugate of 3 minus 2j is 3 plus 2j. The conjugate of negative 2 plus 5j is negative 2 minus 5j. The conjugate of 6j is negative 6j, because look, this is 6j. If you want to think of it explicitly, I mean, it's already in rectangular form. The real part is unwritten. The real part is 0 plus 6j. So we change the sign of the imaginary part, we get negative 6j. 3 is a real number, right? This is 3 plus 0j. So when you change the sign of the imaginary part, it's still equal to 3. So each real number is its own complex conjugate, and you just get the complex conjugate by switching signs. Be careful, sometimes, you know, they might do something like 3j minus 7, and, you know, we're so used to just changing the operation between the two, but if I wanted the complex conjugate of this number, I'm changing the sign of the imaginary part, so it would be negative 3j minus 7, or I usually write the real part first, so negative 7 minus 3j.